All right, this is where we left off last week. Today's the 20th of November. Does anybody remember when the test is? I'll take that as a no. The test is on Tuesday after Thanksgiving break. Does anybody have any questions about when the test is going to be? All right. So we're going to be started a chapter on engine maintenance. So engine maintenance is taking things apart, inspecting them, putting them back together again. It's also something's wrong with the engine, and you have to take things apart and find out what's wrong, fix it, and put it together again. Sometimes you get to fix things on the outside of the engine, but mostly we're talking about the inside of the engine. So we're going to start with the compressor section. If you have damage to the compressor section, in addition to, obviously you can have engine failure. The biggest cause of things that go wrong with compressors, there's actually two of them. One of them is the compressor blades getting worn out or hit by foreign objects, whether it's over a long period of time, you're flying around where it's dusty and sandy and dirty or smoggy, and things either hit and erode and take away metal off of the compressor section, or smog, for instance. Literally, if you fly your aircraft around, if you're a helicopter and you're flying around in the central San Joaquin Valley or in Los Angeles all the time, smog is getting sucked into the engine, and little tiny particles stick to the inside of the engine, including the compressor, and so the shape of the spinning blades changes. So the engine is not going to perform the way it was designed. The blades are not going to push the air and compress the air the way they were designed. So literally what's going to happen if that shape is wrong, because either things have been sucked in and worn off or eroded little pieces of metal, the shape of the blade's not right, or if smog has stuck to, or salt, if you're operating an aircraft near the ocean, salt spray, literally small particles of salt will stick to the blades. If that adds to the blade, but it also makes the blade the wrong shape. Either of these two things are going to cause the compressor to not be as efficient or as effective as it would be. So to spin it around at the same RPM with the same pressure air and the same temperature of air, it's not going to compress the air as much as it would have otherwise. So if the engine is running at its normal RPM and it's not compressing the air as much, what's going to happen to the pressure of air going into, and it's not just the pressure, but it's also going to be the volume of air. So what's going to happen to the ability of the combustion section to burn fuel? If the air's at a less pressure and I have less volume of air going in there, you're going to have less power. So what's going to end up happening for to get full power have to burn more fuel. Well, if you're getting less air in there, but you're burning more fuel, what's going to happen to the internal temperature of the engine? Less air, more fuel. I know this is tough. Think about it for a minute. What's going to happen to the temperature inside the engine? It's going to go up. So for the same power or the same thrust, the engine's going to actually run hotter. And we're going to notice that by higher exhaust gas temperatures and higher fuel flows just to get the same. If it's a turboprop or turbo shaft, we're looking for torque. And if it's a turbojet or a turbo fan, it could either be N1 RPM or it could be engine pressure ratio. Do y'all know what engine pressure ratio is? Who doesn't know what engine pressure ratio is? Stay seated. Okay, let's try it the other way around. Who knows what what engine pressure ratio is? Stand up. Okay, so so somebody almost tried to stand up. So I'm guessing in Mr. Ritchie's class you haven't had turbine engine instruments yet? Have you covered engine pressure ratio in Mr. Ritchie's class? I'm getting a couple of yeses and a couple of no's. It's on the test, the one that you just had? Engine pressure ratio? But he's shaking his head and says no. Oh, okay. All right. So it's been covered. It's just how well it's sunk in becomes the issue. Go ahead. Yeah, engine pressure ratio is the ratio of the pressure of the air going into the engine versus the pressure of the air going out, and it also includes ram pressure. It's not just static pressure. Yeah, thrust. There's effectively, if it's a turbojet or a turbofan, that is, you're not driving a propeller, you're not driving propeller helicopter rotor blades. There's generally two ways to decide if the engine is producing enough power, and one of those two ways is an engine pressure ratio gauge. So how many people in here, if I asked them to draw, tell me where the EPR probes, engine pressure ratio, the EPR, where are the EPR probes? No, hang on a second. I want to know how many people could draw a stick diagram of a jet engine and say, here's where the EPR probes are. Almost 20% of the class. It is different in some engines. Of course, it's different in some engines. So we're just going to pick one engine. Here's our big fan, and here's our engine core, and here we have the compressor, and we have our turbines. Generally speaking, the EPR probe one would be right here, and then one would be right here. So we'd get air going in here, and we'd have hotter air going in there. So this is engine pressure ratio probes. So I know this is going to be tough. Think about it for a minute. If the engine is operating and everything is, oh, I forgot a major component here. We need a fan. Darn, I almost forgot the fan. That's like, how silly of me. So if this engine is operating, which of these two probes would have hotter air going into it? Say again? The one right after the turbine section, yeah. So now here's the question. Which one of these would have faster air going into it if the engine was at a high power setting? The velocity of gases, which one would be higher? If we include static pressure and dynamic pressure means that air is getting pushed into it. Well, let's back up a second. If we look at the air that's going through the fan, what does the fan do to the velocity of the gases going through it? Does it slow them down? Does the velocity stay the same? Does it speed them up? Speeds them up. Okay, what else does it do to the air going past the fan in addition to speeding the air up? It also increases. Say that again? In the fan, I think you'd be hard-pressed to say it does anything more than like a degree Fahrenheit, if that much. Just the fan, not the whole compressor, just the fan. What? Velocity goes up and pressure goes up. The whole reason you put a big giant fan on a turbine is so you accelerate gases not as fast as the main core of the engine, but you increase the pressure. So the pressure is going to be a lot. So in order to do that, you're going to have to increase the velocity the gas is going through the fan. So the velocity right there is really high. The velocity right here is really high. if, Elizabeth, we do a really good job and we put enough turbines in here to extract out the vast majority of the energy and what's going to happen to the velocity of the gases as the gases go through the turbine section. They'll get slower. And if we do a really good job, if we subtracted out all the energy, what would be the velocity right here? If we got all the energy out, what would be the velocity of gases coming out of the turbine section? 0. Of course, what's going to happen? Is the engine going to run very well if there's 0 velocity of gases coming out of the engine core? If the velocity of gases coming out the engine is 0, how much air can we let in the front? Nothing. So if we don't let any air out the tailpipe, we can't let any air on the front. So we can't reduce the velocity down to 0. But we're going to reduce it down as much as we can and still have the engine work. The EPR probes, it's going to be a ratio of this right here, like pressure total number 2 to this right here, which is going to be pressure total number 7. Yes, they're exactly like a pitot tube. I mean, they may not look just like that. I drew them that way on purpose. But yes, pitot tubes, the airflow going into a pitot tube on an airplane for an airspeed indicator is measuring both pressures added together. It's measuring the pressure due to velocity. So it's really ram plus static. Both of these are measuring ram plus static. Now I put PT2 position. This is a position on the engine. Like PT1 might be here out at the beginning of the intake, and maybe PT8 might be if the exhaust pipe went a little farther. In any case, the smaller the number, the closer it is to the front of the engine. The bigger the number, the farther it is aft of the engine, or towards the aft of the engine. So the velocity can't be 0, but it's going to be slow. So literally, EPR is going to be PT2 over PT7, which is a ratio of engine pressures. And this T right there, that T, and that T right here, this is pressure total. And that equals the ram pressure plus static pressure. You think I got this upside down? I didn't bring my textbook with me. All right. So I'm digressing here because what I really wanted to talk about, I'll look it up and let you know tomorrow, is if your compressor section is either eroded and the blades are not, don't have all the metal they used to, or we've had atmospheric things stick onto them, the shape of the blades aren't going to be correct. The compressor is not going to be as efficient or as effective, and so now the engine is going to have to burn more fuel to get the same power, whether it's torque as a turboprop or a turbo shaft, or whether it's EPR or N1. N1 is the RPM, or sometimes it's the fan. The fan RPM is used to define whether the engine's putting out enough power. So you can clean it. You can do what's called a compressor wash. A compressor wash. How come the word compressor wash isn't up there? So you can do what's called a compressor wash. And I think I have a nice video. Ta-da! 3 of them. There it is.
Everywhere in the air, there's particles. Tiny particles deriving from factories, cars and other means of transportation that can be seen everywhere in our modern society, and those from nature like dust, pollen, salt, etc. Altogether, a lot of particles in every cubic meter of air. Large amounts, in this case up to 245 cubic meters of this air, passes through an aircraft engine every second, and some of the particles get stuck on their way. Particles that impair the engine's efficiency, thereby raising the fuel consumption and the emissions of carbon dioxide and nitrogen oxide from the engine. To treat this problem, GTE has developed a system that cleans the engine without the need of adding any detergents. It's simple, safe, and efficient. A common problem when it comes to cleaning aircraft engines is that the water on its way through the engine is expelled to the bypass duct by the centrifugal forces of the fan section, thereby not reaching the core of the engine. GTE has solved this by using hot water under high pressure combined with nozzles, making the water droplets just the correct size to travel through the engine on the same path as the contamination. This, combined with a swift and easy assembly and the fact that nobody has to work within the hazard areas during the cleaning process, means an efficient, safe and environmentally adapted way of cleaning the engine. To illustrate this, we shall now follow a complete cleaning process of one of the engines on this Boeing 737-600. Please observe that the procedure may be different for different engines, aircraft types and airline operators, and that this demonstration is only an example of how an engine cleaning can be conducted. Begin by filling the cleaning system's tanks with water. If possible, use warm tap water to reduce the heating time. Make sure the water quality is according to the specification in the aircraft maintenance manual. Turn on the main switch and begin the heating of the tanks. When the temperature has reached 60 degrees Celsius, the heating is automatically turned off. During the heating time, you can prepare the engines that are to be cleaned. Open the fan cowl panel. Disconnect the PS3 line at the EEC and put end caps on the line and the EEC connection to prevent water from entering the system. On the flight deck, prepare to dry motor the engine. As this procedure is different for different aircraft, please consult your aircraft maintenance manual for specific instructions.
Has anybody heard of that term, dry motor? Dry as in no fuel, and motor means that, are we going to start the engine if we're just going to motor it? No. In fact, I don't know if you caught it, but they actually pulled the circuit breakers for the ignition as well. Because a lot of jet engines, we're going to get to this next week or the week after, is when you start a jet, when you motor a jet engine and all you're doing is trying to make it spin, when you turn on the starter motor, a lot of engines have it automatically set up, so when you push on the starter motor, the ignition comes on automatically. So that's, in this case, set up. That's why they're pulling circuit breakers, just so the ignition won't come on when you hit the starter motor.
Park the cleaning system at least 5 meters away from the engine inlet and connect the power cord. Mount the water spray nozzle on the lower lip skin of the air intake cowling. Then attach the security strap at the rear flange of the reverser duct and connect the high-pressure supply hose to the spray nozzle. Now everything is set for cleaning of the engine. From now on, it's not necessary for anyone to be within the hazard areas.
So the hazard area he keeps talking about is standing somewhere near the intake of the engine while it's spinning around. And the reason it's a hazard is because if the engine is spinning around fast enough, if the engine's running, it's definitely fast enough to suck you in and pull you or your remaining body parts through the engine. But even if the engine's not running, correction, even if you're not burning fuel, if you spin that engine up to say 5 or 10% RPM and the fan is spinning, it's still like a giant vacuum cleaner. And maybe it would kill you, maybe it wouldn't. But that fan could still, if you walked up to the intake, it could pull you into the engine, even if the engine isn't burning fuel. So this diagram right there is on the side of the engine. It's talking about here's the engine, and it says stay out of this triangle, which is where the exhaust is. And here it's saying stay away from the intake. So you'll notice it goes from the beginning of the intake aft about 5 feet. So don't even get within 5 feet of the engine on the side. And I don't know, I can't see any distances here, but it's talking about staying a long way away. Pardon me? 14 feet? You think that's feet? I bet you this country doesn't do things by feet, but I believe you. It does say, they did say park the water truck 5 meters, which is 15 feet, sort of, close to 15.
Start the dry motoring of the engine. After 10 seconds of motoring, press the pump switch on the cleaning system and turn the pressure regulator until the outlet pressure reaches 60 bar. The specially developed nozzles make the water droplets just the right size to travel through the engine gas path on the same way as the contamination, instead of just being expelled to the bypass duct. This is clearly visible from the rear side of the engine, where a steady stream of water can be seen exiting from the core. After 2 minutes of motoring, stop the pump and the motoring of the engine.
How many people have ever started a car engine? 4 or 5 of you. Okay. Well, if you have never started a car engine, have you ever started a car engine and you've cranked it, but it doesn't start? Anybody? Oh, more. Raising their hands now. You start there, you rotate it, and it goes run, right? And then you try to go, oh darn it, run. At some point, well, let me back up. Starter motors take electrical energy and turn it into mechanical energy or rotating energy. Okay, when you run electricity through a wire, what do you do to the temperature of the wire? You heat it up. Okay, inside of a starter motor, it's made out of some magnets usually, sometimes permanent magnets, and a whole bunch of wires. Yeah. In order for the motor to work, you've got to pump a lot of electrical power through it, and that means there's a lot of wires in there, and if you pump a lot of electrical energy through it, then it's going to get hot. The starter motor's going to get hot. So in fact, if you read the owner's manual of your car, which you probably have, it probably says after you've tried to crank 2 or 3 times, you ought to wait 10 or 15 or 20 minutes before you try doing it again. With aircraft starter motors, there's also similar restrictions. Now on reciprocating engine starter motors, I mean, obviously you're going to want to read whatever the maintenance manual or the pilot. You might have to actually read the pilot operating handbook to see how long it thinks you can crank the starter motor, the electric starter motor, and then how many times you can get it. And then if you look at turbine engines, the smaller ones start using an electric starter motor, and they have very, very, very specific lengths of time that you can run the starter motor, and then very specific lengths of time you have to wait for it to cool down before you use it again. Literally, I have worked on an HH-52 helicopter. It's a single-engine helicopter. I don't know who had it besides the U.S. Coast Guard. It was at an AMT school I taught at. And the engine was up on top of the helicopter, and the starter motor was bolted on at the very beginning of the engine. And you could take the cowling. It had a metal shell around it, and so you could see and touch the starter motor if you wanted to. And literally, a normal start, you would run that motor for 20 seconds. And at the end of 20 seconds, We did this one time. We were motoring the engine. We motored the engine for 20 seconds, and then we stopped, and I climbed up on the scaffold, and I touched the starter. See how hot it was? For me to leave my finger on there for more than a second. And all we had done was run that starter motor for 20 seconds. So typically, if it's an electric starter motor on a turbine engine, there's usually, like it'll say, you can try 3 attempts for 20 seconds each, and then you have to wait for 20 minutes. Because what will happen is the inside of that motor gets so hot, the insulation around the wires melts. And then it'll short out, and then it'll get extra hot. So there's typically, there's always, if it's a jet engine and you have an electric starter motor, and these are the smaller jet engines, including the PT6 we have out here, there's always going to be a limit as to how long a starter duty cycle, this is usually what it's called, a duty cycle, how long you can run it, and then how long you have to wait for it to cool down. How long did they just say they were going to spin this engine around? 2 minutes. If this was an electric starter motor, you would have burned that starter motor out. Now, we're not talking $100 at AutoZone. We're talking more like $1,000 or $2,000 or $5,000 for a starter motor that's this big that runs a small engine. The boss will be very unhappy that you melted the customer's starter motor, because the company's going to have to pay for it. So how do they get around motoring this engine for 2 minutes? Pneumatic, that's right. The starter motor doesn't run off of electricity. It has a motor on it that runs off of compressed air, high volume, high pressure air, and doesn't have a duty cycle on it. So you could, in theory, just spin this engine around and around and around and around and around all you wanted, as long as what? Can anybody think of one problem associated with spinning this motor around? Lubrication, that's exactly right. Lubrication in particular, the engine oil system. Do you really want things spinning around without the oil flowing across the bearings? No, you don't. The good news is, if you motor the engine, all the rotating shafts inside of the engine spin, and that drives the accessory gearbox, and the accessory gearbox drives the oil pump. So if you were in the cockpit and you were motoring the engine while somebody was outside, you would actually be able to look on the oil pressure gauge and see that gauge come up. Now, maybe it only comes up to 5 or 10 pounds per square inch instead of 50, but as long as it comes up and there's oil pressure, you're going to be happy. And in fact, that would be something you'd want to watch out for.
Let the engine soak for 5 minutes. Then repeat the cleaning process once more. 2 minutes of dry motoring with the cleaning system pump turned on after 10 seconds, and then 5 minutes for the engine to soak. Now, for a third time, dry motor the engine with the cleaning system pump turned on after 10 seconds. This time, though, turn off the cleaning system pump after 1 minute of operation only and motor the engine for the remaining 50 seconds. On the flight deck, reconfigure the aircraft for normal operation. As this procedure is different for different aircraft, please consult your aircraft maintenance manual for specific instructions. Remove the end caps from the PS3 line and the EEC connector. Use air or nitrogen to clear the PS3 line of possible traces of water. Do not blow air or nitrogen into the EEC, as this can severely damage the system. Connect the PS3 line to the EEC and close the fan cowl panel. Finally, flush the water from the lube, sumps and bleed systems. Please consult your aircraft maintenance manual for specific instructions. The engine wash is now completed. GTE has...
GTE, they're wonderful.
This video will cover the engine compressor wash on the Citation Mustang. The compressor wash of the PWC...
So we watched a video on doing a compressor wash on a transport category jet engine, a very large jet engine. Citation is a reasonable size business jet, but as far as jet engines would go, you might call it a medium-sized engine.
615 engine on the Citation Mustang is recommended to clean the engine of buildup not removed with a desalination rinse or for performance recovery. Refer to the Pratt & Whitney PW 615F-A Line Maintenance Manual Section 71-00-00-160-808. The equipment required to complete the task is a tank system which can be procured from several sources. The compressor wash wand, part number PWC 69836. The fan blade wedges, part number PWC 66581. And a method to prevent water intrusion into the oil tank during the process. This can be done by disconnecting the breather tube or using a blanking plug, part number PWC 69812. The Pratt & Whitney parts can be purchased through Pratt & Whitney. Also, an approved detergent according to the line maintenance manual is required.
Connect the wash wand to the tank system and adjust the settings until the flow rate is 1.6 US gallons per minute. This can be done by marking a bucket and timing how long it takes to reach the line.
Install the fan blade wedges so that they are about 90 degrees apart. Ensure that the flat part of the wedge is facing the inlet abradable liner. Turn the fan into the wedges to help lock it in. Remove the breather tube or install the blanking plug at the breather port in the exhaust of the engine. Ensure that it is seated solidly. Disconnect the two P3 bleed ports and bag the tubes, not the engine. Support the bleed tubes as necessary. Turn off the bleed air source select in the cockpit. Insert the compressor wash wand so that the tube is in the core and the plastic wedge is against the fan and spinner. Communicate with the person in the cockpit and have them engage the starter for that engine. As it starts to spool, open the valve at the wand and inject the cleaning solution. The person in the cockpit needs to push the starter disengage button after 20 seconds. As the engine is winding down through approximately 5% N2, shut off the flow of water at the compressor wash wand. Allow the cleaning solution to sit for 30 minutes. Communicate with the person in the cockpit and have them engage the starter for that engine. As it starts to spool, open the valve at the wand and inject the rinse water. The person in the cockpit needs to push the starter disengage button after 20 seconds. As the engine is winding down through approximately 5% N2, shut off the flow of water at the compressor wash wand. If cleaning solution remains, then repeat this step again for 20 seconds. Remove the blanking plug or reinstall the breather tube. Remove the fan blade wedges. Verify that the oil sight glass does not show any signs of being fuller than before or discolored. Reconnect the two P3 ports after removing the bags. Complete these steps on the other engine. Perform a normal engine start on both engines and operate for 1 minute at 80% N1 to dry them out. Ensure that there are no bleed leaks. Operate at idle for 5 minutes with the bleed air source off. Shut down the engines. If there are any questions or concerns regarding the compressor wash of the PW615 engine, please contact Team Mustang at 316.
So how long on this compressor wash, if this engine, how long did they motor the engine? 20 seconds. Why not 2 minutes? It's almost for sure it's an electric starter motor, and they're making sure they don't melt the starter motor. Yay, PG6.
Are we ready to rock and roll? compressor wash on this PV6, and it's required for compressor efficiency. And like we were talking about, you have an axial compressor and a centrifugal compressor in what's called the cold section of the engine. So to keep our efficiency of the compressor, we're going to do what's called, obviously, a compressor wash. We're going to use that Turco. That's 6-to-1, and we'll mix it up in the container. But the first thing we want to do is make sure that our wand is clear. The attach point is right here on the airplane, and it rides around with the airplane. And fluid's going to go through the ring, and all we'll do is we'll just put a little bit of water in there. We'll pressurize our container and make sure that everything is free and the holes, the outlet holes, aren't clogged up. And then we'll shut it off, and then we'll mix up our Turco, and we'll do that. So
you should be getting like even pressure
all the way around. Yeah, if you look up in here, you might want to grab the camera, and so people can see, and just inside the engine, you see that wash ring
all the way around it.
Yeah, they call it a deluge ring all the way around, you know, so people can see what we're doing here.
Okay.
And then go ahead and take this hose and just gently hook that up there. I'll put a little bit of water inside of the pressure pot here. And like we were talking about, what he says, if you can drink it, you can put it in the engine, but we're going to use distilled water so we don't get any water minerals and that kind of thing into the engine. So we'll put about a half a gallon in there, and then we'll be cool. Yeah, and then this is going to plug in there. You got that tight?
Finger tight.
Okay. It's made for this job, specifically stainless steel. It's got a good O-ring that seals it. And when you do this, you want to make sure that your O-ring seal is in good shape. I lubricated it here a little bit, so that's going to seal up in here. And look how it's built. Mm-hmm. Pressure is going to pushes it out, and you lock it in there. Make sure it's even all the way around. We're good. Okay. And we'll take our 90 psi, and I'm not sure what it's regulated down right now. But we'll check. Okay, so we're good. So we're going to pressurize it. Yep. And then here's our operating handle that goes about 38 psi. Probably going to drop when you get the load off. Mm-hmm. Now, do you want to put the camera up here? There you go. And all we're going to do, we're just looking for even flow all the way around our wash ring. Here we go. Okay. There you go. Yeah. And that's all we need to see right there.
Okay.
Okay. So we're good here, and as soon as it starts turning, after about 5 seconds, just open your valve. And then after about 20-25 seconds, we'll just do that. We'll shut it off.
So watch you.
Yep, watch me. And we'll be good.
It doesn't look like they had any buckets to catch any of that. You notice our mechanic with the short pants isn't wearing
this is freshwater.
Isn't wearing goggles over his eyeglasses.
Yep.
This guy's not wearing goggles at all. It's only pressurized air.
This is the P3 line heater.
Okay. Oh, a heater, huh?
Yeah. And what this does is it prevents at high altitude. Of course, you have a little moisture in the air, and what will happen is you'll get crystallization in this line. So what they do is they attach. See the electrical lead right here? See that? Electrical lead.
Right.
Okay. Well, it's just a toaster heater is what it is, and it heats this line up.
Yeah.
And that prevents crystallization from going forward into the rest of your
Right.
torque limiter and your buck limiter. It's called DY heater. It's one of the items you check on the annual.
I see.
It's got a circuit breaker inside. Pilot can pull it. I have the circuit breaker pulled right now because this will get very, very hot.
Will it?
And I've tested it.
Is that wrapped then?
It is hooking.
Is it straight wired?
No, I think it's wrapped. I really don't know how they build them,
Yeah.
but obviously impregnated and good
Yeah.
rubber, you know. And that's the purpose of that.
Mm-hmm.
This is the trim stick. This is the trim stick. And what?
Well, this wasn't a great training video because they were just kind of showing, yeah, we're going to do it, through. And I couldn't tell whether they were repeating how many times they did it or whether they were just showing it from a different angle. I still would have put buckets out if I had ever done that before. All right, let's go into comparing. You know what? It's 10:30 till, so we'll pick up this tomorrow.